Hi, everyone, and welcome! Ever thought about the secret language that's buzzing inside your phone right now? Well, it's not magic, it's logic. And today, we're going to decode it. Let's pull back the curtain and see what really makes our digital world tick. I mean, really think about it. You tap an icon on your phone, and poof, an app opens. How does it make all these millions of decisions so incredibly fast? Well, the answer is actually pretty elegant. And believe it or not, it's based on some really, really simple ideas. Okay, so the funda behind all of this is something called Boolean algebra. Now, don't let the word algebra scare you. Forget all those X's and Y's. Here, we're just talking about two numbers, 0 and 1. That's it. Think of it like a simple light switch. It's either off, that's a 0, or on, and that's a 1. This simple two-state idea, this is the bedrock of everything digital. All right, so we have our zeros and ones. How do we actually do anything with them? Well, we use a few basic rules, or what we call operations. Let's get into the three most important ones: and, or, and not. Think of these as the absolute basic ingredients for our entire digital recipe. Let's start with and. The rule is super simple, just like the word itself. For an and operation to give you a true or 1, both of its inputs have to be 1. Both of them. A great example is a bank locker, isn't it? You need your key, and you need the manager's key. Just one key is useless. You absolutely need both to get the job done. And this little chart here, this truth table, shows it perfectly. Just look. The only time the output Y is 1 is when both input A and input B are 1. Any other combination, you get a 0. It just proves the rule we just talked about. Simple, no? Okay, moving on. Next up, we have the OR gate. And this is the symbol for it that you'll see everywhere in electronics. It's got this nice curved shape, kind of like it's open to different options. Now, the OR gate is much more chilled out than the AND gate. With OR, as long as at least one of the inputs is a 1, the output is a 1. Easy peasy. Like if you're trying to get a discount at a cafe, you might need a coupon or your student ID. Either one works. You don't need both. And if we look at the truth table for OR, you can see just how flexible it is. See? The only time you get a 0 as an output is when both inputs are 0. Otherwise, if there's even one 1 in there, the output is 1. A very generous gate, I'd say. And last but not least, for our basic trio, we have the NOT gate. This one's the simplest of all. It's also called an inverter, which is a big clue about what it does. It just flips things. Seriously, it does exactly what the name says. Whatever you put in, it gives you the exact opposite. You give it a 1, it spits out a 0. You give it a 0, it gives you a 1. It's the rebel of the logic gate world. And its truth table is, well, it's about as simple as it can get. 1 input, 1 output. 0 in, 1 out. 1 in, 0 out. That's it. Story over. Okay, so we've got our three basic building blocks, and, or, and not. But now let's talk about something really, really cool. What if I told you you could build everything we just talked about and more using just one type of gate? That's the idea behind a universal gate. So a universal gate is like that one master Lego piece, the one you can use to build basically anything you want. In the world of logic, the two most famous ones are called NAND and NOR. Today, let's just focus on the magic of the NAND gate. And NAND just means not and.
But wait a minute, how is that even possible? How can this one little NAND gate pretend to be all the others, and, or, not? It sounds a bit weird, doesn't it? Well, the secret is all in how you wire them up. Let's start with the NOT gate. How do you make one from an AND? It's ridiculously easy. You just take a NAND gate, and you tie its two inputs together. That's it. Now it acts just like a NOT gate. Put in a 1, you get a 0. Put in a 0, you get a 1. Simple, yeah?
Okay, what about an AND gate? Well, remember, NAND literally means not and. So if we want to get back to a regular AND, we just have to get rid of the not part. We do that by inverting the output. So you take the output of one NAND gate and run it through a second NAND gate that's wired up as a not gate. That second gate just flips the signal back, and voila, you've got an AND gate. And the grand finale, the OR gate. Now this one is a bit of a clever trick. It takes 3 NAND gates. You use 2 of them as NOT gates to flip each of the original inputs. Then you feed those flipped signals into the third NAND gate. I know it sounds a bit complicated, but trust me, the logic works out perfectly. It behaves exactly like an OR gate. Pretty genius, right?
So there you have it. That's the real magic. You can just have a huge box of one single component, the NAND gate, and from that, you can build literally any digital circuit you can imagine. This is a massive deal for manufacturing computer chips, making things way, way simpler. Okay, so we've learned all these rules and seen these gates. But so what? Why does any of this matter? Why do engineers spend so much time on this stuff? Well, the answer comes down to one word: efficiency. You see, the real power of Boolean algebra isn't just for exams. It's a super practical tool. It lets us take a circuit design that might be really complicated and messy and simplify it a lot.
Look at this. It's a perfect example. The circuit on top and the one on the bottom, they do the exact same thing. Functionally, they're identical, but the top one uses 3 logic gates and the bottom one only needs 2. By using Boolean algebra, we can prove this and choose the simpler, better design.
And why does that matter? Well, this kind of simplification has huge real-world benefits. Fewer parts means the chip is cheaper to make. A simpler design means signals travel faster, so your phone feels snappier. And maybe the most important thing for us, fewer components means it uses less power. That means better battery life for your devices and lower electricity bills for massive data centers. It's a win-win-win. I mean, when you really stop and think about it, it's just mind-blowing. Every single thing you do on a computer, watching a movie, playing a game, even a supercomputer predicting a cyclone, it all comes down to billions and billions of these tiny little logic gates, flipping zeros and ones, just following these basic simple rules we just talked about.
It's incredible, isn't it? We started with just 2 numbers, 0 and 1, and a few simple rules. And from that, we've built our entire digital universe. It really makes you think. With this simple but powerful language as our foundation, what are we going to build next?